is going to be the Doppler Effect problems number 22 and 23 on the worksheet that says wave notes and calculations. Once again, number 22 and 23. Before we get into this, these formulas here for the Doppler problems are rather complex because you've got 5 different variables. And so if you could just stop the movie here and write all this down, it's probably a good idea. But this big formula, the F subscript O, stands for the frequency of the observer. In other words, that's going to be what a person listening to the sound is actually going to hear, because it's different than what the source is actually blowing. So let's say I blow my horn on my car and it blows, I don't know, a frequency at 400 hertz. Well, if I'm going towards the observer, that observer is going to hear a higher pitch. If I'm going away from the observer, it's going to hear a lower pitch. And that's why you often hear, cars go by and they go, it makes that like, it goes like this. And that's called the Doppler effect. You also have the frequency of the source, which is going to be F subscript S. It's going to the frequency of the source measured in hertz. In hertz. The V is going to be the speed of the wave. In this case, what we're going to talk about today is sound waves. So usually it's going to be somewhere around 331 if it's freezing outside, 345 if it's room temperature outside. It's always going to be different based on the temperature, and so I'm going to have to give that to you. The velocity of the observer is measured in meters per second. In other words, it's how fast the listener is going. Now, in red down here, I'll put down it's positive if it's going towards the source, negative if it's going away from the source. Just keep that in mind. We'll do a few practice problems with that. And then finally, the last letter is V sub S, which is the velocity of the source measured in meters per second. Once again, positive if it's going towards the observer, negative if it's going away from the observer. So if you didn't get a chance to write all that down, go ahead and stop the video. I'm going to go to the next page here and show you these problems that we can do. Okay, so go ahead and stop it if you need to. Now let's do the train problem number 1. It says that a train is moving at a speed of 40 meters per second. So that's going to be the source. And so I'm going to say that 40 meters per second is the velocity of the source. And it sounds its whistle, which has a frequency of 500 hertz. So that's going to be the frequency of the source, because that's what's making the noise. Determine the frequency heard by the observer. So I'm looking for the frequency of the observer. With a little question mark there. But it's a stationary observer, so that means the velocity of the observer equals 0. You got to be careful with little words like that. And it says the speed of sound is 331, so that's going to be my regular old V. That should say at 273 Kelvin on your worksheet, not at. So let's go ahead and write down a formula here. So the frequency of the observer is going to hear is the frequency of the source. Put in your little brackets. V is plus V sub O on top, divided by V minus V sub S on the bottom. Those are the brackets. Let's just fill in all these things now. The frequency of the source was 500 hertz. I'm then going to put in the velocity of the speed of sound, which in this case was 331 meters per second. Plus the speed of the observer, which is 0 meters per second. Divide that by, once again, the speed of sound, in this case, is 331 meters per second, minus the speed of the source, which was 40. Now, it's a positive 40 because they're going towards each other. And when you end up doing all the math here, you end up getting 568 hertz. Now that makes sense, because if they're going towards each other, the frequency you heard would be higher, so 568 is higher than the horn is actually blowing at 500. So always make sure it makes common sense to hear it. 23 is a little bit challenging because there's so much conversions to do. If you notice, they give you the speeds in miles per hour until it stinks, so we gotta convert all that. So let's start with the ambulance travels at 75 miles an hour, so that's going to be the velocity of the source because it's making the noise. But I'm going to change that 75 miles per hour to meters per second. So let's remember how to do that real quick. Miles is on top, so I'm going to get that to cancel out. I'm going to put 1 mile on the bottom. And I know that there's 1.609 kilometers in a mile, so I'm putting that on top. But I don't want kilometers per hour, I want meters per hour. So I'm going to get the kilometers to cancel out by putting 1 kilometer on the bottom and 1,000 1,000 meters on top. So now those kilometers cancel out, the miles canceling out. So now I got meters per hour. Well, I don't want meters per hour, I want meters per second. So the hours over here are on the bottom. So I'm going to put 1 hour on top, and 1 hour is 3,600 seconds. Now the hours canceled out. You do all the math, and you end up getting 33.5 meters per second to the velocity of the source. Now I got to do the same thing because it says the observer is also moving. So I'm going to say the velocity of the observer is 55 miles per hour. So let's go ahead and put that in here and do the same exact thing. Once again, miles is on top, so I'm going to put it on the bottom. 1 mile is the same thing as 1.609 kilometers. And now I got to get the kilometers to cancel out, so I'll put them on the bottom, put 1,000 meters on top. Got to get my hours to cancel out, so put an hour on top because it's on the bottom over here. 3,600 seconds. And so that gives me a total of 24.58 meters per second. And that's going to be the velocity of the observer. So now I got to figure out, well, what the heck is the observer actually going to hear? Now, I'm getting a little bit more room here by hitting the extend button. So I'm going to use my Doppler Effect formula. Same one we used before. And the frequency of the observer equals the frequency of the source. Put your brackets in. We're going to have the velocity of the sound wave plus the velocity of the observer all over the velocity of the sound wave minus the velocity of the source. So the positives on top and the negatives on the bottom. Now we just fill in everything. So now the frequency of this horn, or the whistle that no, it's a siren, okay, is 400. So I'm going to put in a 400 here. But now the velocity and speed of sound is a little bit different. It says 345 in this column, so I'm going to put 345 here. Plus the velocity of the observer, which we got at 24.58. That's a positive 24.58, not because of this, not because of the plus sign, but because it's going towards each other. Okay. I'm then going to come down here and put a 345 again. Minus, I brought down my negative sign. And it's going to be a positive 33.5 because the ambulance is going towards the observer. Close my brackets out. And so now the frequency that the observer is going to hear when they're coming towards each other ends up being 474 hertz. I need to stop it because my smartboard is locked up. Again. Okay, one last thing now is we got to do the second part of this problem. It says, what are you going to hear when the ambulance is going away from the car now? We're going to do the same exact problem, but now there's going to be two changes in the sign. So I'm just going to put this one right next to this one over here. And I'm going to do the frequency of the observer once again. The frequency of the source is 400. Put in my brackets. 345 is the speed of sound at this temperature. I'm going to bring over my plus sign, but watch what happens here. Since they're going away from each other, I'm going to put in a negative 24.58. And on the bottom, you have 345, bring down my minus sign, bring over my minus sign, but I'm going to have a negative 33.58, I'm sorry, 33.5. Because once again, they're going away from each other. So now the frequency of the observer that you hear when they're going away ends up being 338 hertz. Well, both of those make sense because the siren is actually sounding at 400, okay? But when they're going towards each other, it gets higher at 474. When they're going away from each other, the pitch gets lower at 338. So, that should help you out with doing the Doppler effect problems you can see on the lab coming up. Have a great day. Bye.